Okay, so now that we've talked about balancing chemical equations, we're going to talk about what to do with them in a chemical sense. But before we get into talking about the chemistry, let's talk about some not chemistry. So, as a scientist, right, what is our goal? It's the goal of any scientist. If you said take over the world with giant robots, you would be 100% correct. The goal of every serious scientist. And so, to build these world conquering robots, we're going to need some parts, right? First off, as you can see from the picture here, we're going to need some robot arms, but probably not just one, because who wants a robot with just one arm, right? We want 4 arms on our robots. But arms alone do not make a robot. So we're also going to need some circuit boards because I've heard that, robots have circuit boards. And then, of course, if we're going to conquer the world with these robots, we're going to need a chainsaw because, let's be honest, what robot would not benefit from having a chainsaw? And of course, we're also going to need some flamethrowers, and our friend Elon here helping us out with those. And then the last thing that every robot needs, love. We need some robots with hearts. Now, if we were taking over the world, right, one robot would be great. But let's say we wanted to make 10 robots instead of just one. All right. Now, because we have our recipe here, we can do some stoichiometry and figure out how much of this stuff we would need to make 10 robots, right? Like if we need 4 arms to make one robot, we would need 40 arms to make 10. If we need 2 circuit boards to make one robot, we would need 20 to make 10 robots, and so on, right? And that is exactly how stoichiometry works. It is essentially a recipe that you use to figure out how much of something you need, how much of something you can make, all of those great things. So, like balancing chemical reactions, stoichiometry is also based on the law of conservation of mass, but it also is based on the laws of definite proportions and multiple proportions. And essentially, this allows chemists to make predictions about the amount of products and or reactants in a chemical reaction. So, why would we even care? Well, it allows chemists to predict how much of their product can be made based on how much of their reactants are available. Like, let's say you want to make some synthetic rubies. You would need to know how much aluminum oxide and chromium oxide that you would need to be able to make the amount of rubies you want. It allows chemists also to figure out how much of their reactants will be needed to make a desired amount of product, right? Like say here, you've got pig iron. You need to know how much pig iron you need to make a desired amount of steel. And then, of course, it allows chemists to figure out how much of one reactant will be needed to completely react with a given amount of a second reactant. Let's say, and while I'm sure this will never happen, you spill some hydrochloric acid in the lab, right? You're going to need to know how much base you're going to have to use to neutralize that so you can safely clean it up without, getting a chemical burn. Good things to know. How does it work? Basically, it is taking a ratio directly related to the balancing numbers to convert from one chemical to another. Like in this chemical reaction, we can convert from moles of aluminum oxide to moles of potassium oxide. And see, here we have our mole ratio, which if you remember, it's just the balancing numbers from our balanced chemical equation. And we can use it to make some predictions. So, basic steps. Again, you'll want to write these down, pause the video, all that. First, figure out what you're starting with and what you're trying to get to. I like to label these A and B so that I can keep them straight. Start with what you know. This will be the information that the problem gives you, most likely. That is usually what you know. Then convert from your starting units to moles, right? Because we know that moles are the universal unit for chemistry, so you can convert from moles of one thing to moles of anything else. Just remember that this may be more than one step. You cannot always convert directly from your starting unit to moles. Then, what comes in the middle of every stoichiometry problem ever? You use your mole ratio. This should appear, as I said, in every stoichiometry problem that you will do in this class, or really any other chemistry class, and should be in the form of moles of B over moles of A, or what you are going to over what you started with. And then the final step, convert from moles to your desired units. Again, may take more than one step. And that's it. That's stoichiometry right there. 4 steps. So, simple mole-to-mole conversion. Say we've got this balanced chemical equation, and we ask the question, how many moles of vanadium 7-phosphate can be formed from 2.58 moles of chromium 6-phosphate? Just what you've all been wondering. So, we're going to start with what we know. We know we have 2.58 moles of our vanadium 7-phosphate, which vanadium 7-phosphate and chromium 6-phosphate, right? There's our A and our B. So then we get our mole ratio, right? Because we're already in moles. We don't even have to convert to moles. So moles of what we, oh, sorry. I have my A and B backwards. Let's fix that. Erase, erase. All right, because it's asking how many moles of vanadium can we make with moles of chromium oxide. Okay, so great. 2.58 moles for our chromium phosphate. Now, what we're going to over what we're coming from, so B over A, we have 2 of B, 7 of A. Those come down here into our mole ratio. And then we do some math, and we come up with, we can make 0.7 moles of vanadium 7-phosphate. Easy as that. An example of grams of product. So, we've got this balanced chemical equation here, and we ask how many grams of molybdenum 4-dichromate can be produced with 7.45 grams of cobalt 7-dichromate. So, molybdenum 4-dichromate, right there, that's what we're looking for. We're starting with a number of grams of cobalt dichromate. So steps, start with what you know. We know we've got 7.45 grams of A. Then we convert to moles. So for doing this, we're going to use the molecular mass of cobalt 7-dichromate, which, as you remember, we add up the mass of all the atoms in that molecule, and we get 1,629.76 grams. And remember, we want this to be on the bottom so that grams cancels out. Now we are in moles. We come to the mole-to-mole ratio step, where we take the balancing numbers, B over A, 21 moles of B, 6 moles of A, mole ratio. Then we need to convert to our desired unit, which the question asked how many grams. So we're converting from moles to grams. So again, we're going to use molecular mass, but this time of our molybdenum dichromate. And we've got 486.908 grams per mole, right? Making sure our moles B cancels out. And we do some math, 7.79 grams. Remember, so anytime the number that's not 1 is on the bottom, you're dividing, right? Dividing. Anytime the number that's not 1 is on top, you're multiplying. So that's how you work through stoichiometry problems. Okay, third example. How much of our reactants will be needed to make a specific amount of products? Okay, we've got our balanced chemical reaction here. And our question, how much manganese 7 hypobromite is needed to make 12.32 grams of aluminum hypobromate? So, manganese hypobromate, how much is needed? That is what we're looking for. To make 12.32 grams of aluminum hypobromate. This is how much we know we have something that we need. So we start again with what we know. We know we want to make 12.32 grams of aluminum hypobromite, or hypobromite. So we're going to convert that unit to moles. Again, molecular mass, grams on the bottom so they cancel out, and we're in moles, which brings us to the mole ratio. We take the numbers from our balanced equation, 14, 6, moles of A cancels out, and then we convert to our desired unit. Now, it says how much, usually that is in grams. So we're going to assume it's in grams, and we're going to use molecular mass again, this time for manganese, 7 hypobromite, 726.259 grams. Make sure our units are where they want to be so they cancel out. We do some math, 12.19 grams, and you can check me on that. Okay. I feel like this is the last example. How much of one reactant is needed to completely react with another? So again, we have our balanced chemical equation here, and we ask the question, how many atoms of cobalt 5 phosphite are needed to completely react with 23.28 grams of magnesium 7 chromate, right? So we're asking about cobalt 5 phosphite, and we know something about manganese 7 chromate. So, starting out just like anything else, start with what we know, 23.28 grams. We want to convert that to moles, so we're going to use molecular mass. Make sure our grams cancel out. We are now in moles, so we use mole ratio, and that is going to be B over A. Make sure our moles cancel out again. And then we are converting this time to atoms or molecules. All right, so we're not going to use molecular mass. In this case, we're going to call upon our good friend Avogadro. Make sure our moles cancel out. We're going to do some math. And we find that we are going to need 1.42 times 10 to the 22 molecules of cobalt-5 phosphite to completely react with that much of our manganese chromate. And there we go. That is a review of stoichiometry. Hopefully you all remember how to do that. We will take a look at some other stoichiometry applications in videos that are coming up.